Okay, good morning, future presidents. You guys are getting better. Excellent. Okay, last time we were talking about wheels, and we were talking about how when a wheel is rolling normally, that the wheel does not experience any friction. Okay, and we didn't quite have time to finish that, so let's talk about that a little bit more and get that out of the way. So when a wheel is rolling at a normal speed, so you see that it's got translational motion and it's got rotational motion. And we made the point last time that if you look at any single point on the wheel as it's rolling, that point comes down, touches the ground at a single point. At that point, it's not trying to slip forward or backwards. Okay? The fact that it's not trying to slip forwards or backwards means that there's no need for friction. The friction never gets enacted, right? And so the fact that it's not slipping at that point means that there's no friction, which is why a wheel can roll much further than we could let this go if we just tried to slide it. Okay? If that's a little confusing, let's think about it one more way, why that point isn't moving. Okay, so last time we drew a point on the wheel. Do that every single time. It's a wheel, it's going to roll. Okay, so there we go, that's better. So we drew a point on that wheel and we showed when it's rolling that it comes down, hits the ground at one point and picks back up. And at that point it's not moving left or right, so it's not trying to slip, so there's no friction. Okay. Intuitively, that might be a little strange why that point isn't moving, but it's not that hard. Let's think about it. Let's get this wheel spinning, right? Let's think about the motion of the rim. At the top, the points are moving to the right, your right. At the bottom, those points are moving to the left. Okay? So just the fact that it's rotating means that the points are moving, but specifically the point at the bottom has a velocity in this direction when it's at the bottom point. Okay? Now if we combine that with translational motion, okay, then we've got two motions going on. So that point at the bottom, because it's spinning, is moving to your left. Okay? But there's also the translational motion, which means that point's moving to the right. And when the wheel is rolling without slipping, those two velocities are perfectly balanced to the point where that point on the wheel is the only point that is completely at rest. It's just for the instant it hits the ground, it's at rest, and then it picks that back up speed as it keeps on rolling. Okay, so that is rolling without slipping. If the wheel is rolling too fast for its velocity, for this is the extreme example, right? Doesn't have any translational velocity. It just has rotational velocity. Okay, and if it comes down and hits the ground, then definitely it's slipping, right? This rim is slipping backwards in this direction, which means there's a frictional force acting in that direction. That frictional force is doing two things. First off, it's providing a torque, right? We got a lever arm, which is the distance from the center to the ground. We got a force acting in this direction. So that torque is slowing down the spin. Okay? But remember, force is still mass times acceleration, so that force is also accelerating the wheel to the right. So that means if we just spin it like this and set it down, you'll see two effects on the motion that the friction's having. One's that it's going to slow down the spin, and the other is it's going to accelerate the whole wheel over to the right, so it's going to start taking off. Okay? And you can see how quickly there it got into motion without slipping, right? The friction kicked in really quickly, and now it's just rolling regularly. I caught it. Yes! Okay, so thanks for that little applause there. So the other extreme is if it's not rolling fast enough for the translational motion, right? Okay, and that is this case. This is the extreme of that case. There is no rotational motion. There's just translational motion, right? So if we set that wheel down while I'm moving, okay, it quickly starts rotating. Okay, in this case, the frictional force is acting in the opposite direction. Okay, it's going this way. It's touching here. The frictional force is acting back on it. And in that case, the frictional force is also having two effects. One is it's got a lever arm, it's got a force, so it's creating a torque. That torque will start it spinning. Okay. And the other is that that force is acting backwards and will slow down the wheel if I could do that properly. So let's see. I'm not going to do that very well. You have to believe me on that one. This isn't a very good demo for that. But if I do set it down, you'll see that the friction will start it spinning pretty quickly up to the point where it's not slipping. Okay? So, and when it's not slipping, friction is 0. Okay, that is if it's moving at a constant speed. Now, if we're trying to accelerate, it's a different story. Okay? We accelerate, let's see, maybe I should draw a picture on this one. Okay, during acceleration, there absolutely is a frictional force. It's required in order to accelerate the wheel. So while we're accelerating, friction is acting on the wheel. This goes back actually to a very basic principle, which is not very intuitive unless you've thought about it, unless you know Newton's laws. And that is, how do we move in general? Okay, so we are standing here, never walked before, right? It's not intuitively obvious how we actually move. Okay? We know that if we're exerting a force, which is what we can do, that force is acting on other objects. It's not acting on us. And so the fact we're exerting a force on another object does not necessarily mean that we are moving ourselves, right? The other object's moving. The other object's experiencing the force. So we move, though, because of Newton's third law, action-reaction pairs, right? If we want to accelerate in this direction, then we need an outside force that is accelerating us in that direction. Okay? We can't create an outside force on ourselves unless we exert a force on another object. And we do that by pushing an object in this direction. If we exert a force in this direction on an object, then it's going to exert a force back on us in that direction. That's how we're going to move. And the only force that we have accessible to us is friction. Okay? We move through friction. So when we want to move in that direction, we take our foot and we push it backwards in that direction. We are pushing on the floor. Okay? And when we push on the floor pushes back on us and moves us in this direction. Okay? So the same thing with the wheel. If we want to accelerate the wheel, okay, so we want to accelerate this wheel in that direction. We need an outside force to accelerate that, and the one that we're going to get is friction acting in that direction. Friction acting in that direction has to be from an action-reaction pair, and that action-reaction pair is that we are providing a torque on that wheel. So that's what you do with your bicycle or with your car, right? If we want to accelerate off in this direction, we provide a torque, okay, and that torque is trying to accelerate the wheel actually around in this direction so that it is suddenly engaging friction down here. where it's touching. It's trying to slip. Okay? And as it tries to slip, friction gets enacted, and that friction will accelerate it off to this direction. Okay? So it is actually the friction that causes the acceleration. Okay? And it causes this at this point because it's trying to slip. Okay? And specifically, you know, when it's trying to slip, if it doesn't actually succeed in slipping, then it's static friction that is setting in. Okay? These got these two surfaces. We've got the wheel, we've got the surface, and one is trying to slip over the other one. Okay? And as long as static friction is there, it's going to be opposing it. Okay? It's going to oppose this relative slipping, and it's going to accelerate the wheel forward. Okay, but we learned something about static friction last lecture. We know that there is a maximum static friction between any two surfaces. Once you reach that maximum static friction level, then the two surfaces will start slipping, right? And we showed last time, or I tried to show in the demo, that once two objects start slipping over each other, then the friction actually decreases, right? Static friction, the limit on the static friction is higher than the slipping friction between two surfaces. Okay, so a couple points about this. Static friction sets the maximum acceleration you can have for any wheel or for your feet. Okay? Once you, basically, the maximum force you can have accelerating you forward is the maximum static friction force. Okay? That is why we wear tennis shoes. That's why you don't try to compete in track meets in bowling shoes, right? They have very little friction, and so that actually limits how fast you can accelerate. Whereas tennis shoes, right, especially if they're on another rubber surface like a track, there's a very high level of friction, and it's completely that level of friction that sets your maximum acceleration, how fast you can speed up. So you owe a lot to your shoes for how fast you can run if you're a good athlete. So okay, there is a limit on how fast you can accelerate, and it's set completely by that friction between you and the ground. Likewise, cars. The maximum acceleration a car can have is set completely by the static friction limit between the tires and the ground. 1 second. So the higher the friction between the tires, okay, the larger the acceleration you can have. Another point in that is when, you guys have all seen this, when somebody tries to accelerate too fast and the tires start spinning, okay, that's because they've went past that limit. They went past the static friction limit, and now they're feeling slipping friction, which is lower, okay? And they're not actually, sometimes they're not even moving at all, right? The wheels are just slipping, and they're feeling much reduced friction from what they had if they had tried to accelerate a little bit slower and stayed under the static friction limit. Okay? And same with icy roads. Okay? If you're trying to accelerate on icy roads have very low friction. And so there is a minimum amount of acceleration you can reach before you start slipping. Yeah, there's a question right here.
Yeah, so like in terms of track shoes and increasing friction to give you a greater to accelerate you further or to accelerate you faster, what do those spikes have to do with friction?
So the question is, what do spikes have to do with friction for track shoes, right? So those are like the ultimate friction, right? So there's actually a limit for most materials. Like I said, the static friction force depends on it's different for different surfaces, but most surfaces have a limit in the amount of static friction you can create, which is it's called the static friction coefficient, which has a limit of about 1, which basically just means the highest level of friction you can achieve with most reasonable surfaces, unless you get into really specialized surfaces, is the weight of the object. So my weight is my mass times g, and if I've got really high friction shoes, that means the largest friction I can get is my mass times g, which means the largest acceleration I can do is g, so 10 meters per second squared. So that's if you have really high friction shoes. Okay? So 10 meters per second squared is more than adequate for me to accelerate. But for real serious track stars, especially if there's any sort of moisture on the ground or other sports where it gets slippery, then you might want even more friction than that. Okay? And that's where the cleats come in, or the spikes. So they really are just increasing your friction over what you can do naturally with two surfaces. So that was a great question. Okay. Any other questions? Rolling without slipping. Wheels. Things are turning. Excellent. Okay. Let's move on. Okay, so last week we were talking about work and energy, and we introduced work and energy as a different way of looking at Newton's laws. So remember that work and energy were not fundamentally new concepts. They were derived from Newton's three laws, but they're a very convenient way of looking at Newton's three laws. Sometimes, especially if you can't follow the forces in detail, you can still sometimes calculate the work and energy that are involved. Okay? So work and energy, very useful concept. Remember, work is defined as force times distance. Or a displacement. How far the object moves when you are exerting that force on it. And a very key point is this has no directional information. Work is what we call a scalar quantity. It's not a vector quantity. It has a magnitude, but it does not have a direction associated with it. Okay, so that fact actually means, one second, that we are missing very major components of Newton's third laws. Okay, remember, when we're talking about Newton's third laws, we know there's, for example, the second law, force is equal to mass times acceleration. Both the acceleration and the force have a magnitude, and they have a direction. There's directional information that is inherent in Newton's three laws, which are completely missing from our work definition. Let's see, there was a question. Where is this at? You're good? Okay. Okay, so work and energy, while they're a useful concept, they cannot completely encompass Newton's three laws. We are missing information when we are using just the work and energy to solve problems. Another key point about work and energy is that there's many forms of energy, not just kinetic energy. And so if we're just looking at work and energy, we are not actually completely constraining the motion of objects when we're looking at the forces on them. Okay? So, for example, if I take this ball, right, I can do work on it. I can exert a force on it over a distance, right? But that doesn't necessarily tell you the state of motion of this ball afterwards. So if I was throwing it, right, I give it a force, I act on a distance, okay? And we know that if I'm throwing it in this direction, I'm giving it a velocity, so I'm imparting kinetic energy to it. So the amount of work I did on it is being transferred into kinetic energy. Okay? But I'm also doing work on it just by doing this. Right? I'm lifting it up. I'm doing work on it. I'm transferring potential energy to it. I'm not giving it any kinetic energy. Okay? So the fact that I did work on it doesn't necessarily mean that I actually imparted any velocity to it or gave it any motion. So work and energy, very useful concepts, but they are missing two key points from Newton's three laws. One is the directional information, that the forces are how they're working, which direction they're working. And the second component is the state of motion afterwards, okay, because energy has many different forms, not just kinetic energy. So the fact that you did work on something doesn't necessarily mean that you gave it any speed or velocity. Okay, so we need to define a new quantity that takes into account that information. Okay, remember, work is equal to force times the displacement. So this is the distance it acts through. Okay? Let's think about this intuitively. We know if we exert a force on an object, okay, we are accelerating it. The longer the force is acting, the longer the acceleration is acting, which means the larger the velocity is, or the more velocity we're imparting to it. Okay? So there is, of course, the final state of motion depends both on the amount of force that's acting on it and the time that is acting on it. So let's define a new quantity that depends on the force multiplied by the amount of time it's acting on it. Okay? And we're going to keep the directional information this time. Okay? We're going to remember that this is a vector, so we know the direction that the force is acting on. So we're going to define a new quantity which is the impulse, and the impulse is equal to the force acting on the object multiplied by the time that the force is acting. Okay? Whereas work is the force times the displacement, the impulse we're going to define as the force times the time. And we're going to justify that in just a minute. But important point here is that impulse has magnitude and direction. Okay? It's a vector, which means that we are keeping track of which way the force is acted, okay, in any type of interaction that we have. So we are keeping that directional information, and we're also keeping all the information about motion that's occurred because of that force. Okay? So let's try to justify a little bit why we would define an impulse to be force times time. Let's look at a very simple example. We are just going to push on an object. We're going to exert a force on it over some finite amount of time, and we're going to look at the state of motion afterwards. So let's start with the before picture. Here we've got our mass. Okay, it's sitting on our table or the floor, and it's initially at rest. So its velocity is equal to 0. Okay, we're going to start exerting a force on it. That force has a magnitude, but it also has a direction. It's going off to your right. Okay. So the state of motion, that mass, is obviously it's going to start moving off to the right as well. So we're going to let that force run through a little time. That's supposed to be a little clock. So we've got the force acting through some time. Okay, so it's imported an impulse, what we defined as an impulse, force multiplied by time. Okay, and we're going to come off with the final state, of course, which we know, which is this mass. It's going to be moving off to the right with some velocity. Okay, so now to justify the impulse, we need to do a little bit of equation work. Ooh, I used the wrong board there. I'll do that over here. But it's really simple, so follow with me here. We've got a force acting on that object. Remember from Newton's second law, Newton's second law, we know that force, the force acting on the object is equal to its mass times its acceleration. Okay? But we've got that force acting over this time, okay? And we've defined the impulse as being force times time. So we know that the impulse acting, which is just force times time, okay, that is going to be equal to, since we know that force is equal to mass times acceleration, the impulse is going to be equal to the mass times the acceleration times the time. Okay, stay with me here. We've got the impulse that we've imparted is the product of three quantities, the mass times the acceleration times the time. But now acceleration times time, we know what that quantity is. Acceleration is how fast the velocity is changing. Okay? If you multiply how fast an object that velocity is changing by the amount of time that it's changing, this is just the change in velocity. Okay? And so, let's see. Apologies about my little board screw up there. We'll correct that in just a minute. Okay, so we have got the impulse that we just imparted on that object at rest is equal to the mass times the velocity. Okay, or specifically the change in velocity of that mass, but it started off at rest, so its change in velocity is just its final velocity it's moving with here. Okay, so we have a name for this quantity, which is momentum. Okay, momentum is going to be a very useful concept. In some ways, it is kind of like the measure of inertia of an object, how hard it is to stop, because it includes mass. Okay? But it also has a velocity in there. So it has the directional information, which direction the object is moving. And also, of course, the faster it's moving, we know that the longer it's going to take to stop, or the harder it's going to be to stop. So momentum tells you how hard it is to stop an object. Okay. And momentum is a vector. It has a magnitude, and it has a direction. Okay. And what we just defined was that impulse that we imparted on this object was equal to the change in the momentum. If we exerted an impulse on an object, we changed its momentum. Okay? The impulse was the change in momentum. Okay, so momentum, two key things, gives the directional information, and it tells you how hard it is to stop an object. Okay? So let's look back at this example. We have a mass now. We've given it a velocity, so it's moving to the right. And now let's think about how we're going to stop this object. We want to start exerting a force, obviously in the opposite direction, in order to stop it. So we've got our mass. It's moving with some velocity here that we gave it. Okay, that's our initial conditions there. We're going to exert an impulse back on it to stop it. Okay? And then our final state is just going to be that same mass at rest. Okay, so we need to impart, we need to have a force acting on this object. The force has to be acting over time, so we're imparting an impulse Okay? And the impulse that we need to stop it is just the same magnitude as the impulse we needed to start it in the first place, which is back on this board. Okay? This is the impulse we needed to get it moving. Okay? We need the same impulse to get it stopped, except for it's in the opposite direction. Right? The direction of information is reversed. But it's the same magnitude, okay, of impulse that we need in order to bring it to a stop. It's the same change in momentum, it's just the sign has changed. Okay? The direction has changed. Okay, so, of course, the object, when it comes to rest, it has zero momentum, right? So the velocity is zero. Okay, so we want to impart an impulse to stop it, okay? But the impulse can have any form we want as long as the product of the force times the time is equal to the momentum of that object. So it can be a small force acting for a long time, or it can be a large force acting for a short time. Okay? As long as the product of the force times the time is equal to the momentum of the object, okay, and it's directed in the opposite direction that object is moving, it'll bring it to a stop. Okay? But we get to choose whether we're going to use a small force for a long time or a large force for a short time. Okay, a couple of examples of this. You are catching a baseball. Okay? When you're catching a baseball, okay, there are different ways you can catch it. You might not think about that, but there's true. You could be a total spaz like me, stick your arms straight out and close your eyes. Okay? In which case, that baseball is coming in and it's hitting, and it's stopping in a very short time, okay? Because my arm is stiff, I'm not giving it any time. So the time it takes to stop is very short, which means the force required to reach this impulse has to be very large, right? Now, anybody who really knows how to catch a baseball knows that instinctively, once you've done that a few times and realize that hurts, because the force is really large, is that you let your hand give, right? You basically let your hand move when the baseball is coming in. When you're doing that, what you're doing is allowing the force that you exert act for a long time, which means you're slowing down the baseball with a much lower force, okay? Which means that it doesn't hurt as much to stop it. Okay? But you have the control on that. So large force for a very short time, or a small force for a longer time, if you're letting your hand give. Okay, same thing with airbags. Okay? You're in a car, you're in an accident. There are two ways to stop. Okay? One is you hit the dashboard, okay? Large force, very short time. Or the other is that you hit the airbag, right? Small force for a much longer time. The airbag is letting you extend that force out over a larger time. Same impulse, it's the same amount of momentum that they are stopping, you moving in your seat, okay? But you can control how you stop it, whether it's a small force over a long time or a large force over a short time. Okay, so momentum is an extremely useful concept, especially when we're talking about collisions. Okay, so let's define what a collision is. Okay, a collision, we're just going to define that as anytime there are an exchange of forces between two objects for a finite time. Okay, so two objects here. Let's draw them. Here's our object number 1. Here's our object number 2. Okay. And we're going to let them interact for some finite amount of time. So object 1 is going to be exerting a force on object 2, trying to push it off to your right. Okay. We know from Newton's third law that this force has an action-reaction pair, so that object 2 has to be exerting the exact same magnitude of force back on object 1, but directed in the opposite direction. So we know that the forces that they are exchanging are always equal in magnitude and opposite direction. Okay. Now, if we let those forces act over amount of time, we know that the impulses are also equal in magnitude and opposite in direction. Okay, remember the impulse is just force times time. The forces are always equal and opposite. Okay? The amount of time they're interacting, of course, is the same. So the product of the force times time is also equal in magnitude and opposite in direction. Okay? Now, remember what impulse is. Impulse is the change in momentum of the object that's being acted on. So object 1 is exerting a force on object 2. It's imparting an impulse to it. So it's changing its momentum by some amount, sending it off in that direction. Okay? But the impulses are equal and opposite. So that means that the change in momentum of this mass is the same amount, but in the opposite direction. Okay. What they have effectively done in that collision is that they have exchanged their momentum, or some amount of momentum, between the two objects. The momentum that object 2 has gained in that direction was lost from object 1 when it recoils back in the other direction, and vice versa. Okay, so momentum has been exchanged in this collision. So momentum is transferred between the objects. And the fact that the momentums are equal magnitude and opposite in directions means that the momentum in the system is conserved. The amount of momentum lost by one has been gained by the other. But that's keeping in mind that momentum is a vector quantity. It has a direction. So when we say that object 2 has gained momentum going in this direction, object 1 has lost momentum, but we mean by that is that its momentum has changed in a negative value, which means that it's actually been moved to the opposite direction. Okay? So they've exchanged momentum between each other, but the total amount of momentum in that system is conserved. Okay, so this is an extremely powerful thing to know, because in collisions between objects, we might not know the details of the forces. Okay, they might be very large, they might be variable in time, so they might be very complicated. But this tells us that even if we don't know all the details of the forces, we know a lot about the system before and afterwards because the momentum is conserved. Okay? So if we know how one of the objects is moving after the collision, then we know how the other object is moving after the collision. Okay? It had to have the increase in momentum of the one object had to be taken from the other object, and vice versa. Okay? So let's see some examples of that. The first one I want to show is this classic desk toy. Let's see. Okay, we're down on here. Okay, this desk toy is all about conservation of momentum. And most people, if you've seen this before, okay, you lift one ball and it goes back and forth. Okay, this is actually the most boring way to do this thing, but people aren't very creative unless they're really bored at their desk. Okay, what's happening in this? When we lift this up, all we're doing is giving it potential energy, right? When we come down, what we have is that that ball is going to hit the next one, and it's a collision. And in this case, the collision is transferring all of the momentum of this ball to the next one. Okay? So this one comes to a stop. In order for this one to come to a stop, its momentum had to be transferred to whatever's stopping it, which is the next one. Okay? And then that continues all the way down the chain. Okay? Then this one comes up, okay? And then the collision ends, and then we're just back to kinetic energy and potential energy, right? This is converting its kinetic energy to potential energy, then it's swinging back down, and the collision starts over again. So this is basically we're seeing conservation of momentum when this is going on. Okay, there are a lot of other ways of doing this. So let's look at this. Here we're going to lift up two balls. Can you guys see that? Yeah. So two balls. We've got them coming down with the same velocity, but we've got twice the mass. Okay? So in order to save momentum, conserve momentum, you see we have to have the two balls on the other side. They get kicked up. Likewise, we can do 3. See, I told you one ball was boring. Okay, 4. This one's not intuitive at all, but see momentum being conserved. This one is boring, 5. Good, yeah, momentum's being conserved. Okay, so let's go now with 2 from the opposite side. So we've got these coming in. They've got equal but opposite momentum. They're coming in with the same velocity. So momentum's being conserved. Okay, it's being transferred through the other balls to the 2 on the outside. Okay, see, now you want to get one of these, don't you? Okay, so let's do 2 on one and 1 on the other. So we've got twice the momentum coming in from the right side than we do from the left. And so you see, in order to be conserved, it has to kick out 2 on the right, 3 on the left. Let's do 1 more here. We'll do 3 on one side and 1 on the other. If I can do this right. It gets a little messy there. You guys can kind of see that. This is because it's hard for me to hold 3 of them at the same time. So, okay, conservation momentum, very powerful tool for understanding the motion of collisions. Okay, I've got more demos on this. I need 2 volunteers, and I'm going to go back up here and pick people from the back of the room. You thought you could escape me sitting back here. I want 2 volunteers from this area. Yes, there's 1. I need another one. Don't be shy. I'll start picking people. Yes, please come. Okay, let's thank our victims. Okay, let's see. What's your name? Chad. Chad. Welcome, Chad. I want you to sit in that chair. It's a pretty easy demo, huh? I like your t-shirt.
Thanks.
Berkeley of Physics. Hi, what's your name?
Andrew.
Andrew, have a seat. Okay, you guys, you're going to be my masses. Congratulations. Okay, we're going to do some conservation momentum things. First thing I want you to do is roll back and forth in your chair a little bit, just to sort of get the wheels a little bit loosened up there. Okay, so now when you're sitting on the chairs, I kind of want you to keep your feet up on the wheels so you're not getting your feet involved. Up on the legs if you can. Okay, so hands out. Okay. You guys look nice. Okay, so don't be shy. I'm going to push you a little bit closer. Okay, actually bend your arms a little bit because I want you guys to push. Okay, hold on a second. Okay, Chad. What was your name again? Andrew. Okay, mass 1 and mass 2. So Chad is going to be pushing on Andrew with a force. Andrew's going to be pushing back with the reaction force. Okay, let's go for it. Push. Okay, awesome. Momentum was conserved. It's not done. Okay, good job. Let's do another example of that. You see they both transferred momentum one to the other. Now we're going to repeat that with the rope. Do you have enough there to hold on to? Okay, I want you guys to both start pulling on that rope. So you guys are exerting force on each other in the opposite direction. Ow. Very good. Okay, so once again, momentum is conserved. When they're pulling on the rope, the tension is pulling both of them in. The amount of impulse that was transferred is equal and opposite, so they both start moving. Okay, last part of this. You guys look like you can handle this. Okay, medicine ball. That's pretty heavy, right? What did you guess that is? 25 pounds, maybe? Okay, so let's, are you safe there? I think you're okay. Okay, yes? Yeah, that's a good idea. In fact, let's scoot you a little bit closer to start with. Okay, there we go. Okay, remember, feet up on the legs. There you go, so you guys are pretty free to roll. Okay, so you're going to throw that ball. He's going to catch it. So, Chad, when you throw that ball, you're transferring momentum to it, which means you're pushing that ball forward, which means the impulse is being pushed back on you. So you're going to go backwards. You're going to catch that ball. When you catch that ball, you're slowing it down, which means you're transferring an impulse back on it, and it's going to transfer an impulse on you. Okay, go for it. It's kind of hard to throw it this direction. Scoot your chairs back and forth a little bit. Let's loosen up the wheels again. Static friction, our enemy. Okay, let's try that again. Now throw it a little bit harder. Throw it again. There you go. Throw it back at him. You going to take that? Okay, throw it back. That works a lot better going this way, doesn't it? Yeah. Let's try it one more time. Oh, okay, I think that's enough. Okay, so we should have seen them both rolling thanks to static friction, but okay, thanks guys. There we go. Okay, so conservation of momentum. Okay, so let's do one more example of linear momentum, which is our rifle here. So let's zoom up in here. Okay, so rifle, we have a bullet. It's a very tiny bullet. It's only a few grams. Okay? Very low mass compared to the rifle and the block that we're going to be shooting it into. But when we shoot this bullet out, it shoots out of a .22 rifle like this with a speed of about 500 meters per second. So that means it would travel about a whole kilometer in just about 2 seconds. So even though it has a very small mass, it has a very large velocity. So it has a very large momentum because of the velocity that we impart to it. So this is the exact same demo as the one we just tried to do with the medicine ball, but we don't have static friction here, which is good. So hopefully this will be a little bit more successful. Okay, so that is in there. It is cocked and loaded. Okay. And so let's think about the momentum, since I can only do this once, what's going to happen. So when we fire this bullet, we have a little explosion in there. Okay. That is effectively a collision between the gun and the bullet. The bullet is going to be shooting out in this direction with a speed of 500 meters per second. So a very large momentum off to the right. The outside force that is exerting on that, is effectively the gun, the rifle, which means that the opposite momentum has to be has to be given back to it, the opposite impulse, equal magnitude, opposite direction, which means, of course, that the gun is going to recoil. Okay? This one's 500 meters per second, so the gun is probably, 1,000 times more massive, so it's probably going to be recoiled back with 1,000 times smaller velocity, but still pretty significant, okay, on the order of a meter per second. Okay. And then we're shooting that into just like the medicine ball over here. So Chad, Andrew, okay? So sorry, Andrew. So we have a very large momentum rifle bullet that's incident on this. Okay, so the block, it's a collision. The block is going to be exerting a force to slow it down. The bullet's exerting a force to speed the block up. Okay, so the momentum is going to be transferred, but it's conserved through the whole system. So they don't trust me to pull this trigger, so I have to play with fire instead, which is awesome. Okay, so let's go ahead and get this thing. Let me make sure this is aligned. Okay, we're only going to see this once, so pay attention. Ow, should have given me earplugs for that. Okay, so very large momentum transfer. This is not loaded anymore, by the way. Okay. Between the objects. And this actually, until you get used to it, hurts quite a bit. I know from my childhood days in Kentucky. Okay, so linear momentum. Okay, linear momentum is conserved between systems. It can be transferred back and forth between objects in collisions, but it is it's maintained at a constant value otherwise. It can be transferred. We know that it's transferred in equal and opposite values, which is very useful when you're analyzing collisions. And we know that it is, gives us the directional information. Right? We know that momentum has a magnitude and it has a direction, which is why it's between momentum and energy. Okay? So our idea is not that momentum replaces energy. It's that between work and energy and impulse and momentum, we basically maintain all the key points of Newton's three laws without actually having to look at forces in so much detail. We never had to analyze the details of the exact force exchange between the bullet and the rifle, or the exact force exchange between the bullet and the block, in order to know what the velocities of these would be before and after the interactions. Okay, so linear momentum. Okay, so by analogy, we also have rotational momentum. We call it angular momentum. And remember, we're looking at all of our angular quantities as more or less just direct analogies of our translational quantities, and the same holds true for angular momentum. So we're looking back at rotation once again, and let's just go ahead and define our angular momentum. Remember, linear momentum was mass times velocity. Angular momentum was going to be defined as equal to rotational mass multiplied by rotational velocity. Okay, so the same relative quantities. Okay. And we can also define our angular impulse. Remember, the regular impulse is force times time. The angular impulse is going to be the analogy of that, which is just torque times time. Okay? Torque exerts an angular acceleration, so the longer that the torque is acting on an object, the longer the acceleration acts, so the larger the velocity, angular velocity that's imparted to the object while it's spinning. Okay? Key point of these, just like regular momentum, they both have magnitude and a direction defined for them. And the special key point is that the directional information is conserved for these. Okay, so let's draw the direction on that. Let's draw that on our top. Okay, our basic example for rotational motion. So here's our top once again. And let's say it's spinning around in this direction, so that direction in the board. We know that the top has a rotational mass. Okay. We know, remember our right-hand rule, if it's spinning in that direction, then that means that the angular velocity is directed upwards. Okay. And since the angular momentum is just that angular velocity multiplied by the rotational mass, that means that it also, the angular momentum is directed upwards in this case. Okay, so the angular momentum is directed in that direction. It has the magnitude and it has the direction. Like as if this was spinning in the opposite direction, the angular velocity would be downwards and the angular momentum would be downwards as well. Okay? The direction matters in terms of the spin for an object. Okay, so if we wanted to stop this thing from spinning, then we would have to exert a torque for some given amount of time. So that's an angular impulse. Okay? And just like for linear momentum, if we wanted to stop an object that had linear momentum, we could choose to stop this by exerting either a small torque for a very long time or a large torque for a short time. So we get to control the, how we're going to stop it, how we're going to impart an impulse to it. But the same impulse can be imparted by a large force for a short time or a small force for a longer time. Okay? And of course, to stop it, we have to impart an angular impulse to it. Okay, so the other corollary to, or other analogy to linear momentum, which also holds, is that it's conserved for a system. So angular momentum is always conserved. If you have two objects and one of them starts to spin, the first one starts to spin the second one, then the second one will start to spin the first one back, right, in the opposite direction. The angular momentum that's transferred between them is equal in magnitude and opposite in direction, so it is conserved. Okay, I need another victim, one who's not subject to motion sickness. You, come on down. He said sweet. I don't think so. This would make me hurl. Okay, come on down. Okay, what's your name? Skylar. Skylar? Thanks. Coming down. Okay, Skylar. That's good. Yay, come here. Okay, let's get back in the chairs. I won't have you throw anything at me. Okay, you might want to pick up your drink just in case. No, you're fine. So, okay, let's make sure these wheels are nice and loose, okay? So now you got your feet up. Okay, hands out. Okay, this time we are going to rotate each other instead of pushing on each other. Okay, how do we do that? Yeah, let's try that again. Okay, let's get a little closer. Okay? You guys can do this in dorms. Okay, you ready? You might look kind of funny. Let's see. Let's try it one more time. I think this is a bad floor for this. Okay.
Okay.
Are you ready?
Yeah.
Let's see. You're on this. You're on that right there.
And then I keep hitting that.
Okay.
I'll try spinning. I'll push to the right.
Okay. You're gonna push to the right.
Yeah.
Oh, so we're gonna spin this way. Okay. You ready? There we go. That's better. Oh, I'm glad you picked up your drink. Okay. Good. Okay. So, Skylar was exerting a torque on me, so that was spinning me in this direction. So, from Newton's third law, that meant I was exerting the opposite torque on Skylar. So he was rotating the opposite direction. Okay. We got more examples of this. Come over here. You get the big chair. You get the torture chair. Okay. So, let's see. What do I want to do first? Let's do this. Okay, how much angular momentum does he have? 0. No offense. You're not moving. Okay, we'll move you so they can see you. That looks a little scary with your back. Okay, there we go. Okay, so I'm going to give you some angular momentum. Can you hold this just like this? Okay, so it has to be free to spin, okay? Okay, so I'm going to keep my foot on there so you don't start moving. Okay, I'm going to start this. Oh, I've got to keep it there so you start moving. Okay, so we're going to spin this up, okay? I'm going to try to spin this. Let me try that again. I gave it a bad spin. Okay, you ready? You got it? You're holding on to it, right? Okay. Okay, so now he's got some angular momentum. Okay, he's holding on this wheel. We know that the angular momentum is directed upwards in this direction, right? We'll stop you. Okay, your angular momentum is in this direction. Okay, turn that wheel over. Like that, yep. Okay, so you had to exert a torque on that. Now turn it back. Okay, so what happened there? Let me try to spin it up again. Oh, I stopped you. Okay, let me try to give it a little bit more angular momentum here. You got it?
Yeah.
Really good? Okay, so angular momentum is directed upwards. Direction matters, okay? When he flipped it, he had to exert a torque on that, which meant that the wheel's angular momentum is pointed downwards. In order to conserve angular momentum, he had to pick up a large angular momentum in the opposite direction. Go ahead and flip it. Which starts him rotating. Okay? Now, if you flip it back, you're just reversing that, and you're back to our initial position. Okay? The angular momentum of the system, go ahead and flip it again, hasn't changed. Okay? It's just that in order to counter the fact that he flipped that, he had to pick up a large angular momentum to balance it in the opposite direction. Okay, and let's go back to one more. I'm going to have this. You're going to stay there. Okay. There you go. That's a good demo. You can't turn yourself. Okay, so you got the weights again. Okay, angular momentum, key point. Angular momentum is rotational mass times rotational velocity. Okay. If I start spinning Skylar, I'm going to impart angular momentum to him. Okay. And it's going to stay conserved. Hold them in close. Okay. So, actually put them up far. I take it back. Okay, he has a rotational mass. Okay, I'm going to give him a rotational velocity. So now he has an angular momentum. And the cool thing about this is he can change his angular mass by pulling his arms in. Go ahead. But that decreased the rotational mass, so in order to conserve angular momentum, the angular velocity had to speed back up. And if you go ahead and put him back out, you'll slow down. Yeah, it's hard to push him out, right? Okay, go back. There you go. So angular momentum is being conserved in this case, but it has the cool feature that we can change the rotational mass by pulling those in and out, which means you can change your angular velocity. Now, if you want to stop, you should put your arms out. There you go. Now you're a lot easier to stop, huh? Okay. I would be hurling at this point. There you go. Thank you, Skylar. That is all. Okay, this is the exact same. This is the exact same Skylar demo, but here we've got two masses on these rods, and I'm just going to do the exact same thing to show you. I pull up on this, and it'll let me bring it in. So I'm going to rotate it. Okay, and if I pull up on this string, the masses are going to come inside. Okay, you can see it speeds up, and if I let them back out, it slows back down. Let me start that again. I'll do it in the opposite direction, so in case you think that the cosmos has conspired to make one direction unique. Okay, faster because I've decreased the rotational mass. Slows back down when it goes out. Okay, angular momentum, just like linear momentum, is conserved and transferred between objects in a collision. If there's no outside forces acting on a system, then the angular momentum is conserved, which doesn't mean angular velocity is necessarily constant if you can change the rotational mass, like Skylar was doing by pulling his arms in and out. You might wonder if the same is true for linear momentum. Remember, linear momentum is mass times velocity. In an isolated system, the mass times the velocity, the momentum is always constant. Okay? There's not a really good way to change an object's mass. Okay? So we can change its rotational mass by changing the distribution, right? But the regular mass, not so easy. Except there's one case where it kind of is that way, which is rocket ships. This is how they accelerate. And we're going to talk about that, I think, in a couple of weeks. So I think that's all I've got for today. So next time we're going to start talking actually about energy again. And then we'll talk about springs. So see you guys on Thursday.